Okay, here we are for lab 3. We're going to talk about quasi-likelihoods today. And, part of the reason that we're doing this is to draw attention to the connection between score functions and likelihoods. And quasi-likelihoods are pseudo-likelihoods. They're likelihoods that you're essentially going to make up from. It's going to turn out to be a score function. So the basic idea is this. We tend to think of ourselves as modeling and first generating a model. Here the y's are IID, Poisson, lambda, and from that model we can construct a likelihood, take the log, take the derivative, and get a score function. And then we use that score function to get the maximum likelihood estimator, among other things. So we're going to explore the idea of actually doing this in reverse. Specifying the score function, integrating it, right? And then exponentiating it to get a likelihood. And this is quite possible, but the caveat is that not all quasi-likelihoods are true likelihoods. And we'll see this as we go through. So here's a Poisson model, y1 through yn, IID, mean lambda, variance lambda. And of course, the likelihood for this model is just the product of the density. And I can take the log of this. I can take the log so that I get these sums. And I'm summing over all these denominator constants here. Log lambda, right? Because I get a log, yi log lambda. So I get a sum of those things. Minus n lambda at the end. And if I go ahead and then I take the derivative with respect to lambda, this first piece goes away. There's no lambda. I have log lambda times a constant. So I get constant over lambda minus lambda. So this is what I get. And to get the maximum likelihood estimator, what do? Well, we set this thing equal to 0, of course, right? And then we solve for the lambda that allows this thing to be 0, right? So find the lambda such that this thing is 0. And that, in this case, is just y bar. And so y bar is the maximum likelihood estimate. All right? So let's see if we can reverse the process a little bit and, if that's possible and how that might work. So the quasi-likelihood approach needs to start somewhere because there's no model. And so what it says is instead of specifying the model, I'm going to specify some moments. All right? So how about if I specify the first moment and the second moment? And that's it. Now if I specify all the moments, then I have a distribution. But here, I'm only specifying the first two, leaving the higher order moments unspecified. So I'm adding in some flexibility. The nice thing about this particular setup is that the expected value of y is equal to lambda. And everyone's got their own mean, so it's like a regression setting. Your average response will depend on your covariance. And the variance, of course, is equal to lambda I because it's Poisson, it's count data. But I added in here an extra dispersion parameter, sigma squared, and that helps make the model a little bit more flexible. Quasi-likelihoods do that. This is a common thing to say with quasi-likelihoods. So the score function now I'm going to set is y minus lambda over sigma squared lambda. All right? And just so that we can sort of see what this looks like, okay? And of course you have to sum over all the observations. So this is a score and it's sub q, so it's quasi-likelihood. So if you look back here, this is very close to what this looks like, right? This would be y minus lambda, right? Times n over lambda. So if you pull the summation out, it's y minus, so this looks like the sum of the y's minus lambda n over lambda, right? And I can pull the summation back out and get yi minus lambda, right? Over lambda. So that's almost what we have here. Very close, except I got an extra dispersion parameter down here. And so if I want to get back from the score function to the likelihood, I have to integrate first. So I'm going to integrate, and I'll talk about the limits of the integration in a second. I'm going to integrate over basically lambda here, and I'm going to sum over all my observations. And I can do that in this case, and it'll get me back almost directly back to a Poisson likelihood, except I have this constant here, this sigma squared left over. And what makes quasi-likelihoods hard, and it sounds like a great idea, I'll just specify the first two moments, is that there's not always a likelihood at the other end, A, and B, it's hard to figure out what the right integration is, because you're integrating along a particular path in order to get back. And so there are some well-known cases that are worked out, but in general, there was no easy solution. And so people use quasi-likelihood for some specific cases. We're not going to talk about how you determine the path of integration and things like this. We're going to ignore those details and just assume we know them. So here's the plan, or the quasi-plan. Do you get it? Yeah, I hope so. I can hear you groaning. So I'm going to set the quasi-score equal to 0 and solve for lambda I, and I'm going to get a maximum likelihood estimate for that lambda. And then I got to estimate, I got one more parameter, the sigma squared. And so I'm going to use a traditional old estimate. I'm going to take y, divide by the mean, scale it, and square it. And this is going to be an estimate. And this is a very common way to estimate the variance. And so number one yields quasi-MLEs because you're finding the estimate that maximizes the quasi-likelihood. And number two is a pretty standard moment-based estimator for the dispersion parameter. It looks like a scaled variance, basically. Okay? And so one thing that you may ask is, well, why bother, right? What's wrong with the plain old Poisson model? And the answer is that when you look at count data, very often the mean and variance are not equal for the count data. And so you have either over or under dispersion. But this Poisson assumption where the mean and the variance are the same is an assumption that's often broken. Here's a very simple example to see how that works. Suppose I have a Poisson model, just a plain old Poisson model, basically. I got one group. You can think of it as one group. The y's are Poisson, and I'm going to use mu here just to mix it up, use a different symbol, and we'll see why later. And I'm going to use this model. I'm basically going to treat all of these n people as coming from one group. But suppose in reality what happened was you actually had two groups. Maybe you had males and females, and you were counting something like car accidents. Males have many more car accidents than females, for example. And you group them all together and you ignore gender. Well, it could be that each group has a underlying Poisson process, that the counts for group 0 follow a Poisson distribution with mean 0, lambda 0, and the counts for group 1 follow a Poisson distribution with mean lambda 1. But when you put them together, you're going to get over dispersion, because you don't have a Poisson process anymore. And you can see that by just calculating the conditional mean, the marginal mean and variance. So what's the expected value of y? And now in this group here, what's the expected value of y? Well, some proportion of people are from group 1, and some proportion of people are from group 2. So that's going to be my new mean, the weighted average of the two means. And I'm going to just define this to be mu, which is why I'm using mu here and not lambda. Well, what about the variance in this group? Well, the marginal variance is the expected value of the conditional variance plus the variance of the conditional mean, right? So the variance of y given z, okay, would be lambda naught when you are in group 0, right? Or lambda 1 when you're in group 1. Right? And I can take the expected value of that thing, right? This is the variance here. And then the variance of here we want the expected value of y given z. Well, if you're in group 0, you get lambda 0. If you're in group 1, you get 1. So I want the variance of that thing. And so you can then just go ahead and compute these things. Okay? And you get all these terms. These are correlation terms here. You got cross product terms. You got a little bit of everything. And I can rearrange it. And I rearranged it so that it looks like the mean plus some extra. And there are several ways to rearrange this, but this is, I think, the most intuitive. So that now this process, which you happen to assume is Poisson, okay, is not really Poisson anymore, because the mean is mu and the variance is mu times 1 minus some delta. All right? So the mean of the working model mu is a weighted average of the group means. The over dispersion factor, okay, this 1 plus delta is going to be estimated by sigma squared in the quasi-likelihood setting. And then this last little piece down here is the covariance. All right? And so the basic idea is that while you may assume your data are Poisson, but if you fit this model directly, you're not going to get a good estimate of the mean because you're forcing the mean and the variance to be the same. And this could happen simply because you forgot to include a particular covariate. That's important. And so what happens is the process that you actually observe, the marginal process, the process that ignores that covariate z, looks like it has extra variance. Because you have a group, and one way to think about it is you have a group where you see some counts in here and it has some variance. You have another group up here, higher counts, so higher variance. So both these, the mean and the variance, are the same. Mean and variance are the same here, except now if I take the whole thing, as a group, I'm having trouble with the mouse, take the whole thing as a group, then I get extra variance because they're spread out. All right, let's just do the regression example. I want to work through this because I am going to take some time to actually run through the code that's in the Lab 3 Dropbox, where I'm going to talk about, and I'm going to fit some of these, and we're going to talk about them. But first, I want to make sure that everyone understands what these models are. So these models are essentially, this is essentially a generalized linear model where you're modeling the mean, the log mu, which is the log of the expected value of y given the group that I'm in. And I'm going to let that be beta 0 plus beta 1z. And so when z is 0 and you're in group 0, I'm going to get beta 0 is equal to log of lambda 0, right? So lambda 0 is going to be e to the beta 0. Okay? Now, turns out beta 1, okay, is going to, beta 1 is important because when z is 1, beta 1 then changes the mean. The mean becomes beta 0 plus beta 1 on the log scale. Right? And so the log of the difference is the difference of the logs, and you can show that beta 1 is, the log of a ratio is the difference in logs. And so you can show that beta 1 is actually the log ratio of means. And so this is going to be the log rate ratio. And if you haven't already done this in Andrew's regression class, it's worth just working through and deriving what these things are. It's just a little algebra. But this means these two things are telling me what the contribution from the first group is and the second group. So now I want to write down what the likelihood is, right? And so the likelihood is e to the minus lambda to the x over x factorial. Well, here the x's are our data, so y. So you got y, y. And e to the minus lambda, well, this thing is lambda, right? Isn't it? Right? So when z is 0, this is e to the beta 0. That's lambda 1. When z is 1, okay, this is going to be e. This is going to be e to the beta 0 plus beta 1, which will turn out to be lambda 1. And the same thing happens here in this piece. And this substituting regression parameters for means is exactly how you come up with a maximum likelihood estimator for regression settings. Then if I want the log likelihood, I just take the log of this expression, and this follows, right? Take the log of here, the e comes down, this ends up here, this comes down, and it's pretty straightforward. Now, in contrast, the quasi-likelihood looks almost the same, except I've got an extra piece right out here, 1 over sigma squared. And so I can maximize this function, or I can maximize this function, okay? Now, in this case, because these are complicated expressions now, there are no closed forms for maximum likelihood estimators or quasi-maximum likelihood estimators. All right, but one thing that's nice is estimation of the over dispersion parameter doesn't affect estimation of the betas. And the way you can tell that is because you can multiply, this is a constant for this log likelihood, and I can always rescale this by a constant. So if I'm interested in beta, I can rescale this by sigma squared, and that's not going to change the beta that maximizes this function. All right, so the difference here is that one method specifies a working model. That's the quasi-likelihood. It's only giving you the, The difference here is that one model specifies a working model, Poisson. And that model may or may not be correct, depending on how you model the data or depending on what you know about the process. The other is really only, the quasi-likelihood is really only trying to specify the moments, right? And it starts by using a score function. And these methods imply slightly different likelihood functions, so you get slightly different answers. And in 1 second, or in the next video, I'm going to show you how we do this in R so that it's clean and clear and you can see what's going on. Before we jump over to that, I wanted to give you the general form. So in fact, quasi-likelihoods do have some generality, and you can actually get quite a lot of different regression models out of them. And so you have the y's. I'm going to assume that their mean is sigma squared, and their variance, let's try again. The y's have mean mu, and their variance, okay, is equal to some constant times a function of the mean. And I'm going to assume that constant is unknown. And we'll see very clearly why this would make sense. In the Poisson case, right, you could have sigma squared equal to 1, and then the mean could be mu, and the variance function could be the identity function. So this, you could have let this be sigma squared times mu. And then you'd get right back to the Poisson model when sigma squared was 1. So you write down the score function. It's easy to write in a general form, and the log likelihood then is the integral of that thing. Some properties, the score function is 0. The variance is sigma squared times this thing. The expected value, okay, of the derivative of the mean, so this is like the second derivative is equal to that variance. And you can always estimate the over dispersion parameter here like this. Okay, and this is just a regular chi-square estimator of the over dispersion. We take n minus the number of parameters that you have, and you have y minus its mean squared over its variance, like a standardized variable squared, which would be something would be roughly normal. Squared is going to be chi-square. That's kind of the idea. So if in fact you let the variance function be 1, okay, your quasi-likelihood is going to look like this. Y minus mu squared over 2 sigma squared. This to me looks like the kernel of a normal distribution, right? Mu sigma squared. It's very close. And in fact, these two things will give you the same thing then. If you let the variance function equals mu, then you get what's very close to a Poisson likelihood, except you have that over dispersion parameter. If you let your variance function be mu times 1 minus mu, then in fact you end up with something that looks like a binomial distribution. with a dispersion parameter out front. And if the variance equals mu squared, you get something that looks even a little bit weirder. And this, I think, is related to a gamma regression. All right, so we've sort of gone over the basics, and hopefully you get the idea. We're going to fit some of these models in the very next video.